Morning students, I hope that you are keeping well at your home in the time of lockdown and you are concentrating on your studies. So now in this new video of electrostatics, we are going to start chapter 2 of the first unit, that is electrostatic potential and capacitance. So in this chapter, basically we are going to study electrostatic potential. This is another effect of a static charge in its nearby surrounding or in its nearby space. And second, capacitance. Capacitance is capacity of a conductor to store electric charges. So in this chapter we are going to study about these two quantities. So first of all, what is electrostatic potential? Electrostatic potential is defined as line integral of the electric field between infinity to a point of the electric field. So if or this same quantity can be defined as the amount of work done to move a test charge, that is unit positive charge, from infinity to a point of the electric field without any acceleration. So that amount of work is actually line integral of the electric field. We can define work of a force as line integral of the force with respect to path of displacement. So similarly, if unit positive charge is being moved from one point of the electric field to the other, it's going to be either potential if the charge is being moved from infinity to that point, or a potential difference if the charge is being moved from one point of the electric field to the other. So let W work is done to move Q naught charge from infinity to point P of the electric field. This is point P. Suppose this point is at infinity. At infinity, electric field of this source charge, whose electric potential or whose electric field is existing in this space, its electric field is 0 at infinity. But as soon as test charge is brought inside the electric field of this source charge, either this source charge can do the work to move the charge by its attraction if the source charge is suppose negative, or work can be done by some external agency if the force of the source charge is repulsive. So in that condition, potential at certain point of the electric field is going to be positive. If the source charge is negative, work is being done by the source charge due to its attraction, then potential of the charge is going to be negative. Suppose W work is done to move Q naught charge from infinity to point P of the electric field, then the electrostatic potential at point P can be given as V is equal to limit Q naught is tending to 0, work done divided by magnitude of the charge. So that SI unit of the electrostatic potential is Joule Coulomb inverse, or this is also called volt. So volt is the SI unit of electrostatic potential. How you can define 1 volt potential at a point of the electric field? If 1 joule of work is done to move 1 coulomb charge from infinity to a point of the electric field, then potential at that point is said to be 1 volt. This is SI unit. In CGS unit, potential is expressed in stat volt. Now what can be relation between SI unit of the potential and CGS unit? 1 volt is equal to, we know, 1 joule divided by 1 coulomb, and that is equal to 1 joule equals 10 to power 7, or divided by 1 coulomb equals 3 into 10 to power 9 stat coulomb. So relation between volt and stat volt is 1 volt equals 1 by 300 stat volt. Here we can see the CGS unit of the electrostatic potential is 300 times larger than its SI unit. After defining electrostatic potential at a point of the electric field, what is potential difference between 2 points of the electric field? Here you can see in the electric field of this source charge, there are 2 points, point A and point B. If a test charge is to be moved from infinity to point A, certainly amount of work is going to be greater. But if the test charge is moved from infinity up to point B, work is less. Therefore, potential at point A is greater than potential at point B. So what is going to be the potential difference between these 2 points? If a test charge is being moved from point B to point A without acceleration, that would be the potential difference between these 2 points. So potential difference between point A and B, VA minus VB, can be written as limit Q naught tending to 0, work done divided by magnitude of the test charge. So we can see what can be the SI unit of potential difference between 2 points of the electric field. SI unit of the potential difference is same as unit of the potential, and CGS unit is again stat volt. What can be dimensional formula of potential at a point of the electric field or potential difference? Dimensional formula of the work, m L to power 2 T to power minus 2 divided by dimensional formula of Q naught, that is current multiplied by time, and dimensional formula of the electrostatic potential or potential difference can be written m L to power 2 T to power minus 3 A inverse. So electrostatic potential due to point charge. Suppose positive Q is a point charge. This charge is not distributed over any length, volume or area of cross section. Simply its dimension is very small as compared to other distances. In that condition we can consider Q as a point charge. So in the nearby space of point charge Q, there is point A, this is point B, distance between point A and point B. Now we are going to find what can be the expression for the electrostatic potential in the electric field of a given test charge, given point charge. So for that, suppose there is a test charge at point A whose distance is x from the source charge positive Q. So what is force acting on the test charge at point A? It's going to be a repulsive force away from the source charge, and that is given as F is equal to kq by x square. The value of k 1 by 4 pi epsilon naught if the medium present around the source charge is air. Now what can be the work done if this test charge is to be moved from point A to point B? That work done can be written as force experienced by the test charge multiplied by displacement dx cos 180 degree. Cos 180 degree displacement is taking place opposite to direction of the force. So this would be the expression dw is equal to minus kq divided by x square dx. Now what can be the work done to move the test charge from infinity? As we have defined potential at any point of the electric field to be the amount of work done to move test charge from infinity to that point. It means we need to find electrostatic potential at point C of the electric field. It means we have to find the amount of work done to move a test charge from infinity to point C. The distance of point C is suppose R from the source charge. So what can be the work done if we integrate the previous equation, integral 0 to w dw equals minus kq integral infinity to r x to power minus 2, value of 1 by x square can be written x to power minus 2 dx. So after integration, the quantity is going to be minus kq multiplied by minus 1 by r with limit infinity to r. After putting value of the constant k, that is 1 by 4 pi epsilon naught for air, and value of the limits, upper limit minus lower limit, it comes out to be minus kq into minus 1 by r plus 1 by infinity, and 1 by infinity is equals 0. Therefore, potential at point C of the electric field is written as V equals 1 by 4 pi epsilon naught for medium air Q divided by R. Here from this formula you can see potential at a point of the electric field of a point charge. V is directly proportional to magnitude of the charge Q, and it is inversely proportional to distance of the point R. V is directly proportional to Q and V is inversely proportional to R.